Okay, hi everyone. So before we get started with this week's speaker series, I just wanted to let you know about an event that's coming up, and this is one of the events that can be counted towards your participation mark in Sci 113. So this is the science case competition, and it's taking place in November. So it's an evening event, November 6th, 5:30 p.m. And basically what this involves is working together as part of a team to research and try to come up with some solution to a real world scientific problem. At the moment, the topic has not yet been released, and it will actually be released to the groups like 10 days before the event date. And so then everybody has the same amount of time to research the topic and to put together a presentation with a solution for the case study competition. I won't go over all of these details, but I just wanted to let everyone know that the registration deadline is October 21st. And so if you are interested in taking part in the science case competition as one of your options for participation in an event for Sci 113, please do register by October 21st. So I'm just going to stop screen sharing here, and I will put a link to that in the chat. I will also follow up in an announcement to the Canvas course. But yeah, I think that's probably enough from me. So over then to our guest speaker, Dr. Nadine Bourdois-Dedekind.
Okay.
Yeah, thank you. Thank you, Dr. Bourdois-Dedekind. I'm just going to jump in with a couple of announcements first, and then I'll introduce you in a moment. But it's great that we've got your screen shared and it looks great. So welcome everyone to the third lecture as part of our speaker series. Of course, just a few reminders. It's great to see many of you joining live. For those of you joining by live stream, hello. But also for those of you that are watching the recording at a later time, I just want to recommend for everyone either here live or watching at home or watching at a later time, do think of some questions that come to mind during today's talk, just to get some ideas about the scientific topic of today. We're going to hear some really fabulous work from our guest speaker today. And as a reminder, there are worksheets associated with each of the seminar. And if this is one that you watch and feel like you want to contribute to and submit by Saturday at 10, that can be part of your score for the speaker series, and you are expected to complete 4 out of 6 worksheets over the course of the term. But just as a reminder, it's important for everyone to engage with the presentations, watch them, and so that you can debrief them in the next class, as well as have these topics available for you relevant to your final project at the end of the term. So with that, it's my pleasure to introduce our speaker for today, Dr. Nadine Bourdois-Dedekind, who is an expert in atmospheric chemistry. She completed her PhD at the University of Toronto and postdoctoral fellowship in Europe at the Swiss Federal Institute of Technology in Zurich. Here as an assistant professor at UBC in the Department of Chemistry, her group studies how chemicals in the air change over time and how these changes affect air quality and climate, and looks at how tiny particles in the atmosphere help form ice and clouds, which has huge impacts on weather and climate and all these great things. So I'm really looking forward to your talk today, and thanks again for joining us.
Great. Thank you, Marcia. I really appreciate the introduction. Hi, everybody. My name is Dr. Nadine Bourdois-Dedekind. If you are in my Chem 121 class, you call me Dr. Bourdois. That's great. And so now I get the chance to talk to you about the research that I am doing as a research faculty member in the Department of Chemistry here at UBC. So what I want to do, I have a 3-part series for you. I want to first introduce to you the topic of atmospheric chemistry. And then I want to talk about how this field got started and the role that ozone hole has. And then the last part is mostly going to be about my research, looking at air pollution, forest fire, smoke pollution, and indoor air quality. So I hope that sounds good. Thumbs up. And let's get started. So I'm a chemist. And when I think about the atmosphere, there are different components that I take into consideration. So, for example, if you're doing your chemistry labs, you are, using beakers and Erlenmeyers. And the way I think about the atmosphere is a very similar way. I just think that the atmosphere is this sort of really large beaker that a lot of molecules are reacting together. So for example, we have these molecules that we can introduce into our beaker, and this is my big atmospheric chemistry beaker. So these are molecules that are emitted. For example, I've drawn here alpha pinene, and this is a molecule that's emitted from pine trees. And then ozone, for example, which is an oxidant. But we have lots of molecules, right? Even think about every time you smell something, that's an organic molecule that's interacting with your nose. So it could be super smelly, it could be good like flowers, and all these molecules are being emitted into the atmosphere and then have opportunities to react. So one thing that is really key about thinking about the atmosphere and the molecules that we're breathing is that they're very often in the gas phase. And what is unique about the gas phase is that it's really governed by radical chemistry. And you would have learned in Chem 121 that radicals are very, very reactive. Why? Because they don't have their octet rule met. And when we think about molecules in the gas phase, they're not like liquid phase where they hit each other all the time, or solid phase where they're very close together. In the atmosphere, the molecules are very far apart. And so every time they hit, which is quite rare, for there to be a reaction, we needed those components to be very reactive. So very much governed by radical chemistry in the atmosphere, and that's a lot of the work that we do. We study radicals. So for example, light can photolyze O2 into an oxygen radical that can then form ozone. And in the stratosphere, this ozone is very good ozone. But then there's a lot of other radicals like this hydroxyl radical or this nitrate radical that also continue to oxidize the molecules in our troposphere, so very much closer to Earth, and that causes problems. So ozone down low in the atmosphere is actually bad ozone. And I'll give you some more examples as to good ozone up high, bad ozone down low. Okay, so we have our, oh, did I forget to animate this? Oh, let me go back a moment. I wanted to show you my comparison with the two flasks that, you know, when we put our flask on a heat plate to warm up the components in our flask, well, the equivalent of the heat plate in the atmosphere is the sun, and that's providing energy to the system. We can also have a stir bar in our beaker, and this stir bar is mixing everything. And so what's the stir bar in the atmosphere? It's the wind, and it mixes all the molecules that are there. And so this helps us understand, you know, I'm kind of giving you a hint into how I perceive the atmosphere to be, and all of these components mixing each other. And so you can imagine there's a lot of chemistry that can happen. Okay, so I talked to you about radicals. And the other thing that can happen in our atmosphere is we have a lot of surfaces. Not only the surfaces, for example, indoors where we have our furniture, or outdoors we have windows that get very dirty, right? Or buildings, but we also have tiny, tiny particles in our atmosphere, and they're called aerosols. And this is what I'm calling heterogeneous chemistry. And it's kind of equivalent to, like, let's say a catalysis using palladium. But the idea is that on these surfaces of these particles, we can also have a lot of chemistry that can happen. And this is now heterogeneous chemistry because it's not only in the gas phase. And there are lots and lots of particles actually in our atmosphere. And my next slide is showcasing 3 different types of aerosols or particles. Smoke particles, so you see them here. Where are they coming from? The West Coast. We are right in the middle of this smoke plume. Sea salt, so this is now sodium chloride being emitted from wave action, for example. So this is in blue. And then we have dust. And so dust, you can see from the Saharan desert, is lofting up all this mineral into the atmosphere, and it can be a reaction vessel for a lot of chemistry to happen. So I have this animation here. It's from NASA. And you can see how these particles are moving across the hemisphere and also mixing together. You can see here how the sea salt aerosols are mixing with the dust aerosol, making a complex chemical mixture that has really important impacts on cloud formation. And you can see here now the dust spreading across almost all of Canada, not the dust, but the smoke spreading all over Canada. So this is just to show you that the chemistry also needs to, like as atmospheric chemists, we also need to include chemistry that can happen on the surfaces. Another thing I think a lot about as an atmospheric chemist is water. Water is my favorite molecule, and I think it's just such a fascinating molecule. It exists in the atmosphere in the gas phase, in the liquid phase, and in the solid phase as ice. And so those phase transitions are very interesting and impact climate, of course, because where we have clouds is also where we can reflect solar radiation. So we definitely think a lot about water in the atmosphere, and that's the key solvent to consider. And to prove that, I have an image of the global cloud cover model, and everything you see in white are clouds. So this is either liquid water or ice. And you can see it also evolve over the Earth, and this is ever changing, and knowing how to predict this is also very important. Where the cloud in the atmosphere forms is important for radiative balance. And so there's a lot of research and understanding how these little cloud droplets, for me, act as mini reactors, chemical reactors, where there's a lot of chemistry that can happen, especially when you start to inject forest fire smoke into this mix. So the last thing I want to add to my kind of analogy of the atmosphere as a beaker is light. And the light source is very important because the light that we get on Earth from the sun actually is above 290 nanometers. And so when we think about photochemistry, so chemistry that is driven by the sun in our atmosphere, we have a set wavelength that we look at and consider for them to be atmospherically relevant. So above 290 nanometers. And so that kind of limits also how much input we can have into our system. So as an atmospheric chemist, I care about the atmosphere. I care about the molecules that we breathe. And I would argue there are two key reasons why you might also be interested in thinking about atmospheric chemistry. The first is air pollution. What is it that you're breathing, and how is it problematic for your health? And also for crops, for example. And then second, how do the molecules in our atmosphere impact climate? Especially in a changing climate, the chemical composition of our atmosphere is changing. And I'll give you a quick example. For example, increased temperatures also means more molecules in the atmosphere. And how does that burden of molecules impact or accelerate the change in temperature, for example? So I'll give you two contexts, air pollution. I'll give you a couple of examples about why this matters. And then I'll give you an example about how we link atmospheric chemistry to climate. So first, for air pollution, I outlined three different concepts. So first is particulate matter exposure. And what that means, it's the particles that you breathe in and what effect might they have on your body. And there was this very famous study that was published in 1993. It's called the 6 US studies. And each letter here corresponds to a town or a city in the United States. And what you see is that the mortality rate ratio as a function of fine particulate mass, so micrograms per meter cubed, there was a direct correlation. The more fine particulates there was, the larger the mortality rate ratio. And that was such a key study because it perfectly identified that there was a causation here between fine particulates and mortality. And maybe for sure a relationship and the causation, like you still needed to kind of say why, but it really kind of started a very important field in looking at aerosol impacts. And I think since COVID, we've also become even more interested and appreciative of how these aerosols are moving, especially indoors, and how we can be exposed to these different aerosols. The other one is toxic molecules. So specific elements or specific molecules that can have an impact on our health. So for example, methyl isocyanate is a molecule that was emitted in the 80s in Bhopal, India, from a chemical industry. And this molecule is so toxic that when that gas was released, it killed over 1,000 people who just happened to live in that area and breathe those molecules. So understanding how these molecules behave, because you can't see them, right? So what are you breathing? So that's an important component of air pollution. Radioactive material. So for example, we have radioactive material like radon that can come and seep through the soil. And then that's a radioactive element that can be present in your basements, for example. And this is also true in some places in British Columbia. So we want to understand, how are these radioactive material behaving in the atmosphere? Mercury is also an example of an element important for air pollution, because in the biogeochemistry cycling of mercury, we have coal power stations that emit mercury into the gas phase. And for example, I'm the site operator of an air quality monitoring station at the top of Whistler. And if you're familiar with Whistler, this is the peak chair on top of Whistler Mountain. And our station is right below the Lifty Hut on the right. And we measure mercury that comes from the outflow of Asia that traverses through over the Pacific, and then we detect it in Whistler. And that gives us information about how mercury is traveling through the atmosphere and also what its fate is in the atmosphere. And then I also like the story about sriracha sauce. I like sriracha sauce, and there was a plant in California a few years back that had a filter malfunction and ended up emitting a ton of capsaicin into the atmosphere. And residents nearby complained of itchy eyes and itchy throat and went to the emergency room. And it was really because they were breathing these molecules that are part of the process of making the sauce. So what I'm highlighting here is that you can be breathing particles that can be problematic, and you could be breathing pollutants that are also problematic for your health. And the way they're problematic for your health is to cause oxidative stress. And so I've outlined some molecules here, the nitrate radical, the hydroxyl radical, some of these aerosols, ozone, and they stress your system, and then that has responses into your cardiovascular system, links to all these different diseases, including pulmonary diseases. And I think a context that my group works on that is also very relevant to us living in British Columbia is our exposure to forest fires. And so in my group, we look at what are the molecules inside the fire. And as the fire goes up into the atmosphere and starts to travel downwind, how is the chemistry of that smoke changing as a function of time, as a function of exposure to the sun, as exposure to water when it forms a cloud, and just aging and processing to different oxidants as it moves through the atmosphere. And you can imagine that that's important for understanding what we're breathing, because if you're breathing a fire or smoke from a fire at the source versus if you're breathing smoke that has traveled 100 kilometers downwind, which is worse? And that's an active area of research, both in my group, but also in the community, to try and identify and propose policies to say, well, what should we do when we're very close to the fire in terms of exposure, or when we're exposed to fire that has or fire smoke that has traveled through the atmosphere? So that's the air pollution point. So now let me go to the climate point. And what I have here is a graph showcasing radiative forcing as a function of agent, or as a function of CO2 or methane or aerosol radiation or aerosol cloud interactions. In red, we see a positive radiative forcing. So that would lead to increased temperatures in our climate. And then aerosol radiation and aerosol cloud interactions are actually tend to be cooling because they can reflect radiation back out to space. So when you add up all of this information and you try to predict what a forcing might be onto our climate due to our increases in CO2 and increases in methane and also increases in aerosols, you get definitely a positive warming effect. So this is a positive anthropogenic forcing. But look at how big the uncertainty bar is. And this uncertainty bar doesn't come from the CO2 uncertainty bar or the methane. Those are very small. This very large uncertainty bar comes from the aerosol cloud interactions and the aerosol radiation interactions. And so there's a lot of people, including my research group, looking at reducing these error bars so that we can better predict what these effects might be in our changing climate. So overall, what that means, thinking about atmospheric chemistry, is it's really a stool with 3 legs. And one leg is field studies. So in my group, we take some of our instruments and we go outside and we measure the real atmosphere. We can also put our instruments onto an airplane and fly, for example, through a smoke plume to understand the chemical composition. We can put our instruments on a ship and look at emissions from the ocean. We also put our instruments on a van and we can drive around Vancouver and look at where the smelly parts in Vancouver might be. So we can take our instruments out into the field. So we do a lot of field campaigns, they're called. But we also do a lot of laboratory studies because very often the atmosphere is very complex. And so if we want to understand one single molecule or one single oxidation process, what we can do is take that molecule and bring it into our lab and study it. And so we actually have a big beaker, big atmospheric bag in my lab, and we can then inject known molecules and study its chemical reactions and processes as a function of time or sunlight exposure, for example. So the lab studies help to inform the atmospheric models because we then use models to predict what the overall effect might be from a climate change perspective, but also from a chemical transport model perspective. So if there's an industry that emits certain amines, for example, and that's based on what I did during my PhD. So these are pollutants, but then what happens is downwind, they get oxidized to amides, and then they get oxidized to isocyanates, which are even more toxic. So predicting, how many kilometers downwind of this chemical industry, we should probably not build a city because people might be exposed to those molecules. But we also need to think about mitigating, even though the amines are less toxic, we still need to make sure they're not emitted because they become toxic in the atmosphere. So what that means, back to this image here, is that these field studies connect to the lab studies, connect to the modeling studies, and they're very interconnected. So our research in atmospheric chemistry ends up being very interdisciplinary. We work with meteorologists, with computer scientists, we work with engineers, we work with mechanical engineers, electrical engineers to build these instruments. We work with chemists and physicists. And I really like that because I love to learn and I find it a very interdisciplinary field. So that's my little introduction to atmospheric chemistry. And I might like to pause here and see if there are any questions about how I think of the atmosphere before we go on to the second phase of the talk. And maybe, Marcia, you can help me see if there's any chat questions.
Yeah, I'm just looking at the chat now, and feel free to raise your hand if you have any questions so far. or perhaps all of that's still percolating and you can save them up for the end, but we'll just give it a moment and see if any questions pop up.
Okay.
Oh, Sierra's got a question. Go ahead, Sierra.
Hey, hi, Sarah.
Hi, thank you so much. I guess I know it's still the introduction. I guess I'm curious, like, what's your main motivation behind these studies? Like, is it most specifically about human health, or is it more from like an environmental perspective? Or
Yeah. Yeah, great question. So I'll skip ahead and I'll give you a little overview of my specific research interest. So this is an overview of the research in my group. So for example, we're very interested in molecules that we breathe when we're indoors. And we have studies looking at perfumes and those molecules and how they change over time and how they react with your clothing. And then how you are actually impacting ozone air pollution outdoors because of those molecules. So those molecules, that's really an air quality context, because those molecules don't, in the grand scheme of things, are not really going to impact climate. So that's an example where there's a research project that's much more geared towards the health aspect. But for example, in my group, we're very interested in how forest fire smoke affects cloud formation. This is this atmospheric ice nucleation component. And so what we're trying to understand is how do the molecules from the plant combustion, whether that's the lignin, the cellulose, or the hemicellulose, how are these molecules impacting cloud formation? And we're finding that they're actually very effective. So there's more clouds, they last longer. And so this is really important for climate. For air pollution too, because you want to know the molecules that you're breathing, but this I think has much more of a climate impact because we still don't have a good theory to predict exactly which aerosol is going to make which ice cloud at which temperature. And so we're trying to think, okay, as chemists in this field, and there's a lot of atmospheric physicists and meteorologists and engineers in this field, and we're kind of the token chemists because we can tell the community, okay, which molecules are important for ice nucleation and how these molecules are arranging to template the ice formation and that phase change. So those are two examples from a health and from a climate perspective. And then I also have my favorite element. So my favorite molecule is water. My favorite element is selenium. And we started looking in my group, and we're probably one of the only ones doing this well, for sure in Canada. And I think there's maybe one other group in Switzerland that looks at atmospheric selenium. And so we're really building new instruments to look at the very small concentrations of selenium in the atmosphere. And the concentrations are very small. So, if you go and sniff some algae, which has some selenium emissions, you're not going to die. But we want to know how selenium is transported, and that's going to inform how selenium distribution over the planet matters. And because selenium is a necessary nutrient, so it's an essential nutrient, like too much of it is problematic in your diet and too little is problematic, then it has that connection with health. And then same with looking at the forest fire oxidants, that's also from a health perspective. So do you see how I'm trying to say, okay, this is an atmospheric chemistry problem, and we study because we care about the molecules that we're breathing, but also because we care about the molecules that are impacting clouds.
Yeah, thank you so much.
Yeah, you're welcome. And I see also there's a question in the chat.
Yeah, that's right. Can you see it?
Yes, I see it. It's in front of me.
Okay, perfect.
So Eric asked, how do aerosols affect and cause reactions? And I absolutely love this question because what I can show you is an instrument that we have in my lab. And okay, let me show you what my lab looks like to answer that question, Eric. So, I have the flask and I have all these different processes that are happening in our flask. And this is my lab here at UBC. We have a chamber and it's 2 meters by 2 meters by 2 meters. so 8-meter cube, and we can put specific molecules inside and study how they behave. We can also put aerosols and study how they behave. And aerosols can be made of mineral dust, they can be made of sea salt, they could be a combination, they can be organic molecules from forest fires, and they can be all three. So a very complex mixture. And the more complex, the more interesting for chemistry. And so we have this specific instrument, Eric, that's called a scanning mobility particle sizer. And what this instrument is this part of the instrument, it actually is an aerosol sizer. So it's going to say, oh, your aerosols are 100 nanometers in diameter. They're 200 nanometers in diameter. Oh, they're 500 nanometers in diameter. So we can look at how the aerosol is either shrinking or growing as we run our experiments. And then this part of the instrument is a counter. So then it's going to tell us, okay, we actually have 2,000 particles in 1 centimeter cube that are 100 nanometers in diameter. So with this information, we actually get a size distribution of the aerosol size and number. And this is an experiment where we were cooking Brussels sprouts in the lab. And what I'm showing as a function of time is the experiment. And then the y-axis is the diameter. So as we go up the y-axis, the particles get bigger and bigger and bigger. And then the heat map is the number of particles. So when it's red, we have more particles. When it's blue, we have fewer particles. And so you can see that there's like no particles, no particles, no particles. And then exactly at this point in time here, we started to cook Brussels sprouts. And you can see all the aerosols that were made. And what we reported in this paper earlier this year is that those aerosols from the Brussels sprouts can actually make a certain type of oxidant called singlet oxygen. And no one had observed the formation of that oxidant before in an indoor setting. And so we were able to kind of flag and say, hey, there's another oxidant that we've identified in indoors that is something we should think about and better understand how it's formed, what its impact might be when we breathe that oxidant. So this is an example of how Brussels sprouts, so aerosols, can impact oxidant formation and therefore have an implication for our exposure when we're cooking. And my advice about that is to turn on the fan when you're cooking, so you're not exposed to so many of these aerosols. So I hope that answers your question, Eric. Yes, okay, great. Okay, so that being said, and it seems like there's a little bit more interest in my research program. So I'll just do a very quick overview of how the field of atmospheric chemistry got started. And it got started actually because of the discovery of the ozone hole. And the key molecules responsible for the ozone hole are these chlorofluorocarbons, CFCs. And these are man-made molecules. They don't exist naturally in the atmosphere. And they're used in refrigeration and also in these like can sprays, aerosols. And they were used in large quantities, but they actually have no fate in the atmosphere. So they don't transform in the atmosphere is what I should say. And so they just accumulated and accumulated and accumulated into the atmosphere. And we have data from many different sites around the world in different hemispheres, the North Hemisphere and the South Hemisphere. And all of these different locations, including Mauna Loa in Hawaii, where the concentrations of these CFCs were just increasing. And what was happening was these CFCs were going to the stratosphere. And the stratosphere is up around like 4 to 60 kilometers straight up. Like that's way further than where planes travel. And these molecules were then going to the ozone layer and interacting with the ozone layer and destroying the ozone layer. And that was identified by Mario Molinera and Sherwood Rowland in 1974. And they got the Nobel Prize for this discovery. And what they discovered was that under UV light, up in the stratosphere where the wavelengths are actually a lot shorter. So if you remember, E equals hc over lambda. So we have shorter wavelengths. It means we have higher energy. And they were able to destroy those molecules and release chlorine radicals. And then the chlorine radicals destroy ozone. And so these scientists in the 70s were like, oh, you know, this is problematic. This might be affecting our ozone layer. And then scientists went to the ozone layer and saw that it was decreasing, that the concentration of ozone was decreasing, and that's what we call the ozone hole. But I also want to draw your attention. So this paper won the Nobel Prize. Take a moment to read the title very carefully. Do you see a typo? Atom catalyzed? Right? So there's a typo in the title. And, you know, so don't stress too much. You can still get the Nobel Prize, even if there's a typo in your title. So I like to tell the story. So the chemistry really involves these ClO, these chlorine oxide radicals. And what was so astounding when they put instruments on a plane, and this is a paper from 1989, and what they saw was that this is the ozone concentration. So you see the ozone concentration mixing ratio is here. It's high, 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 high. And then when you get very close to the pole, it drops. So the ozone concentration decreases. And what is so remarkable is that the exact same time and location, the ClO radical actually does the complete opposite. And so that was indicative of a field campaign that supported a lab study that showed that these chlorine radicals were destroying ozone. The more ClO radical you had, the less ozone you had. And the reason that this is specifically done in the Antarctic, I'm happy to answer questions about that, but it's because it's so cold down there, and we get the formation of polar stratospheric clouds, and these clouds also impact the catalytic cycle of the chlorine destroying the ozone. So in all, this was really kind of fascinating, and only very recently, and okay, well, recently, 2016, was there concrete evidence in a paper published in Science that the Antarctic ozone layer was healing. And that's a really great success story, because it tells us that the Montreal Protocol, which is the treaty and the policy that was in place to prevent the formation of these CFCs, or the prevent the release of these CFCs, was very effective. So, so what I want to play for you is this YouTube video. It's narrated by David Attenborough, and it's describing the benefits of the Montreal Protocol in reducing the amount of CFCs and healing the ozone layer. So let's watch that together. Oh. Okay, and hopefully you can
Let me share
hear.
with you one of the greatest success stories of environment negotiations ever. Indeed, it may be one of the greatest success stories of any sort of negotiations on this planet.
In our long history, there is one unprecedented act of humanity in which every country on Earth came together to protect the future of life on Earth. The Montreal Protocol.
The story of the Montreal Protocol is in some ways also the story of the 20th century. Something that was a great invention, namely a chemical chlorofluorocarbon, had unintended consequences that suddenly became a planetary problem.
It all began with a good idea. In the 1920s, coolants in refrigerators were so toxic that a leak could kill you. So we invented safer chemicals to do the job, CFCs.
The wonder chemicals of the 20th century.
They were so versatile, people's lives were transformed. But in 1974, Sherwood Rowland and Mario Molina predicted that the Earth's natural sun shield, the ozone layer, was being eaten by CFCs at a terrifying rate.
We felt a great responsibility to actually warn society that something could happen.
All eyes turned to the ozone layer. And sure enough, there was an enormous hole in the stratosphere.
Such a shocking revelation. Over half the ozone layer destroyed above Antarctica in a decade.
If the destruction wasn't stopped, we'd be at risk from lethal levels of UV radiation.
We'd be in dead trouble. We'll have a blind, burnt population.
Faced with this global threat, the world came together to take action. And in 1987, more than 30 countries agreed to phase out the production of CFCs and signed the Montreal Protocol. Over the 3 decades since, the rest of the world's nations have signed up. Together, they've taken on the greatest planetary repair job ever attempted.
It's absolutely terrifying to work on a project that's so important because you know that failure is not an option.
Making the Montreal Protocol a success has taken brilliant minds.
We are working to protect human life.
It has taken determination.
It has made more progress than any other environmental invention in the world.
If the countries of the world engaged in similar deliberations for every issue that faces our world, I'll be very happy.
And it has taken ingenuity from an extraordinary global community.
We always have our disagreements, and at the end of the day, we have our agreement.
And it has worked. With CFCs banned, the ozone hole is healing. Now it's time to take action again.
You need passion, you need leadership to change the Montreal Protocol into an even better treaty. Victory is within our grasp.
There's only one Earth. We have only one Earth to protect. We cannot lose this one.
All right. So I like this video. It's very short, very powerful, very emotional, I think, as well. In thinking about how atmospheric chemistry, so lab experiments, were able to predict a potential catastrophic impact on ozone. And then lots of scientists went to observe, found that fact, and then the community came together to address that fact. So I'm happy to see if there's any questions about the ozone hole or about these policies that I could maybe help answer.
Yeah, Talia has a question in the chat, and then Ahmed has his hand raised. So maybe, do you see the chat there, Nadine?
I do. I have it like
Okay.
yeah, I didn't close it, so I have it in front of me.
Perfect.
Okay, so Talia, you asked, how do scientists like you, so I guess me, who play a significant role in protecting air quality in the environment for the benefit of public and environmental health, view large corporations and agencies that operate in ways that undermine the preservation of global and human health? Yeah, this is a loaded question, Talia, because it has a lot of different components, right? And the first one is capitalism, economics, people's livelihoods. You know, many industries that are polluting also provide services. So as an environmental chemist, as an environmental scientist, I'm not a fan of pollution, you know, like I'm trying to understand it so that we can better mitigate it. But it's also important to understand that this is very, very complex issues. And they often involve politics, they involve money, corporations, scientists, indigenous peoples, and there are a lot of different stakeholders in many of these discussions. But one thing I can do, Talia, is to give you the example of the CFCs, which is really, you know, the refrigerant industry. Do you think the refrigerant industry was happy about having to regulate CFCs? No, they were not happy at all. And they were opposed to the Montreal Protocol because they were gonna not make a lot of money, right? They were gonna lose money through this. And so think about the oil and gas industry. The oil and gas industry that is emitting a ton of CO2. We know that that's a problem. We know that that's causing anthropogenic climate change. And then you say, why are we, you know, why is the Paris Agreement still being debated? Why did it take so long to get us to do a Paris Agreement when people in like over 100 years ago were predicting the effect of increased CO2 concentrations in the atmosphere and were warning? There are papers in the 1920s that tell us about this problem. This is over 100 years ago. And unfortunately, the answer is money and political power, because the refrigerant industry didn't have the same amount of money and political power as the oil and gas industry has. They have a lot of money. They have a lot of power. And so it's a lot harder to go against these powerful and rich people. And that's sad. I think that's really, really unfortunate scenario, right? Because we do have the science available to know how to tackle CO2 emissions and reduce them. And then it's political will, and we can, I'm happy to talk a lot about this. But yeah, these are complex, very complex societal issues, and I hope that many of you are interested in tackling these. You need a lot of intelligent people with diverse skill set who can communicate. And as an academic, so as somebody who's affiliated to a university, I like this position because I can speak as an independent researcher. So I can point to the mining company, you know, or the oil and gas and say, you are emitting this much CO2 and it's having this effect and this chemistry and this reaction and this reaction. Now they're going to be like, oh, look, Dr. Bordois says this, who cares about her, you know, because I'm not a government and I can't impose sanctions on this problem, but I can help draft policies to address those issues. And this is a big part of my job as a professor here at UBC, is to translate what we're learning about the environment and the atmosphere into policies. So yeah, I think I could go on, but I hope that gives you an idea of like, yeah, these are complex issues, and capitalism is definitely a big part of these issues. Okay, Ahmad. Hi, what's your question?
Yes, hi, Professor. Yeah, that was great. I just had a quick question. I was wondering, so you mentioned the ozone hole and formed towards the south, like over Antarctica. So is there some kind of similar effect happening in the north since of the temperature as well?
Very good question. I have a slide for you, Ahmad. So what happens for this chemistry to happen, for the ozone destruction, is we need very, very cold temperatures to form these clouds. So you see, these tend to be very colorful. They're very high up in the atmosphere, and they're all ice, and they have a lot of acid in them. And these only form if you're very, very cold. And Antarctica gets colder than the Arctic. And it gets colder because Antarctica is an island. And so you get what's called a polar vortex that basically isolates the Antarctica island, and it can get very, very cold. So because it's colder there, that's where we saw the biggest hole in ozone. And the chemistry that was generated this is at the surface of these clouds. They're called polar stratospheric clouds. They're made of lots of acids, sulfuric acid, nitric acid. And then what was happening is these chlorine radicals from the CFCs. So all the Cls that you see are from the CFCs. And then what happens is they react on the surface of this cloud. They form Cl2, chlorine gas. Now, remember, in Antarctica, they go 4 months with no sunlight, right? It's dark for 4 months. So this chlorine, what happens is it builds up and builds up and builds up because there's no light. And then the light comes up in the spring, and that's September for the southern hemisphere. So in the springtime, and then there's just this burst of chlorine radicals that just eats up the ozone. So actually, the ozone hole is one only in the spring, because after that, those chlorine radicals, they settle or they react, and they're no longer, like they can go into HCl, what we call reservoirs, they can go into ClO and O2 molecules. So there's fewer and fewer of these radicals as the summer progresses. And so the ozone cycling can continue. So the ozone hole is actually only in the springtime, and it's only at the poles because it's so cold. But here's another problem that addresses your question. What we've observed, and this is a paper from 2020, is that increased CO2 in the troposphere is causing the stratosphere to cool. And now the Arctic stratosphere is getting colder and colder and colder. We are now detecting the first instances of polar stratospheric clouds, and that means ozone destruction. So we have now detected an ozone hole in the Arctic. So that's bad news. That's bad news. And so, of course, anything that heals the ozone in Antarctica will also heal the ozone in the Arctic. So we just want to stop, producing any of these CFCs. But yeah, this is a very complex problem. And now it's a combination of the CO2 and the CFCs that are causing this unintentional problem now up in the Arctic. So I hope that answers your question.
Yes, no, absolutely. That was great. Yeah, and yeah, it's unfortunate to hear that we discover something new, but hopefully through like more research and the kind of research you do, we'll find like alternative solutions to this. It's great to hear.
Yeah, I hope so too. I think that's what motivates my life as a professor.
Yes,
for
absolutely.
sure.
All right. Thank you.
Marcia, how are we doing on time? Can I take I know there are a couple of questions.
Yeah, I think I think in this last answer, you may have touched on, Maya's question there in the chat about, kind of specifically where ozone holes are forming. But Matthew has a question about kind of where in the atmosphere ozone is formed. And yeah, maybe you could address both of those. We're good for time. Absolutely.
Yeah. Okay, thanks. Thanks, Maya and Matthew. So Maya, I think I helped explain why this is chemistry that's really happening specifically at the poles in Antarctica because of that cold temperature. And I have another image I can show you here. So this is the ozone. So this is May, and May in Antarctica, that's just the beginning of winter, right? So you see that the ozone concentration is high in red. And so you actually get quite a lot of ozone at this specific altitude, 18 kilometers. And then what happens in the spring, when you get this burst of chlorine radicals because the light of the sun is coming in and photolyzes the Cl2, then you get this chewing up of the ozone and you get this hole specifically over Antarctica, because you see it's very low concentration. And so this is why it only happens during that time of year. And it happens again at the poles because you need those clouds to serve as a catalyst. And so Matthew, your question is, how does it replenish? I also have a slide for you here. So this is called the Chapman cycle. And the Chapman cycle is a suite of chemical reactions that involve ozone formation and ozone destruction. So how you form ozone is you have oxygen molecules in the atmosphere. And then because you're so high up in the atmosphere, you get these high energy, low wavelength photons. And then you can form O, atomic oxygen, and that's going to react with O2. And M just means like a third body. So any other molecule to take in that excess energy. And then you form ozone. But that ozone can also get photolyzed at actually higher wavelengths, so lower energies, and form oxygen again. And so this is what we call a null cycle, because it just forms and breaks, forms and breaks, forms and breaks. But then you can also have ozone react with atomic oxygen to form 2O2, or with ozone itself and form 3O2. So these are reactions that we understand. And then when we add chlorine catalytic cycles in this chemistry, it disturbs this cycle. But it's through this chemistry, the O2 generation here, that we can replenish the ozone. Okay. So in the last then little bit, so about 20 minutes or so, I want to tell you about some specific projects in my research group. And so this is the overview I showed earlier from one of your peers' questions. And I do want to acknowledge that the work that we do, we're very privileged to do this work on the traditional ancestral territory of the Musqueam people. And I also live on campus, so I have the humble pleasure of not only living and working and playing on this land, and I think that's very important, and I'm very grateful. And then the chemistry that we're doing is applied to both health context and air pollution context. And this is a picture of the students in my group, very international group, and I like that, to bring lots of different perspectives and innovations. When we have potlucks, it's always very delicious. And the key challenges that we address is looking at fundamental atmospheric chemistry processes so that we can predict how these molecules are distributed, how they react, and what their lifetimes are. And we look at both the gases and the molecules in the aerosol phase, because that's also what we're breathing. And we have a special expertise in my group where we have organic chemistry tools and analytical chemistry tools. So we're very good at like pushing arrows on reactivity of these molecules and doing mass spectrometry. So that's the expertise that we have in the field of atmospheric chemistry with those three stools, the three-legged stool that I showed you earlier. So how do we study the complex atmosphere? In my research group, we have two approaches. We have the top-down approach and we have a bottom-up approach. And what I mean by top-down approach is we actually go and collect the real atmosphere. So atmospheric collection is what it can be called. And there are different ways of collecting gases and different ways of collecting particles. And I would say that collecting gases is really hard, actually. So the way you can collect a gas is using these canisters that you would evacuate. So there would be like a vacuum inside. You take that canister outside and you open it and it goes, and then you suck in the air inside the canister. You only get that point in time at that location though. So it doesn't tell you so much about all the environment unless you have maybe 50 of those canisters and you go, and then you kind of go and take that sniff from all the different locations. And then you bring the canister back into the lab, and then you can connect the canister to all these different instruments. And we do that with our mass spectrometers, and that we can know what the molecules are inside these canisters. The other way is to collect particles, and that's a little bit easier. And this is a particulate matter sampler. And what we do is we have a filter with very, very small pores that allows the gas to go through, but that collects any particles. So any particles that have a size higher than, let's say, 20 nanometers will get collected onto the filter. So we need a pump so that we're pumping air through. And then we have our filter holder, and then we deploy our filter where we want to sample. So we deploy a lot of filters at the top of Whistler, for example. When there's smoke in Vancouver, we also deploy them outside the window to collect some of that smoke. And then what we do is we take the filter, we bring it to the lab, and then we extract the molecules off that filter. And then we can, study those molecules using all the different instruments that we have access to. And that's this instrument here. So that's a kind of automated filter sampler. And then this is called an impinger. And we have this instrument also in my lab. And instead of collecting aerosols on a filter, it collects aerosols in water. So it has this cone here, and this is a pump that pulls 300 liters per minute. And then through the Coriolis force, the aerosols go in and then get trapped inside this cone. And then we unscrew the cone, and then we can do analyses, chemical analyses on this, on the air that we collected, on the aerosols that we collected. So that's one way. The other way in the top-down approach is, like I said, these field campaigns. And for example, my group has participated in a number of field campaigns. And this is a picture of me and Ayomide, who's a PhD student in my group. And we were part of a field campaign last summer where we deployed our mass spectrometer. And I have this instrument. It's called maybe I have a picture actually. Let me show you my favorite instrument. Here it is. It's this instrument right here. It costs $1 million. It's called a proton transfer reaction, time of flight, mass spectrometer. I think it's the coolest thing. I like to call this instrument the super nose because I can point the inlet to multiple people, to your breath, to your hair outside, and measure in real time the molecules that we see. So every second I can see 1,000 molecules. And so I can track them over time. Every second, what happened? Did it increase? Did it decrease? Did it stay the same? Why? So we can do analyses on these reactions, on the fate of these molecules in real time. So what we did is we shipped this instrument, we sent it to Toronto, and this is a picture of us. So we had a site. So this is this picture here. This is at the top of York University. And we had a collection of about 15 different instruments. So there was like lots of millions of dollars worth of instruments in this room. And we measured urban air quality in real time for 4 weeks straight. So imagine I'm seeing 1,000 molecules every second, and then we watch what they do for 4 weeks. So it's a lot of data. So there's a lot of data analysis that we have to do. But what was super cool with this campaign is that we also had collaborators with NOAA and NASA in the United States, and they had the same instrument that we were operating on a plane. And they flew over Toronto, and they flew over our site, and they did these twirls so that we could look at the molecules as a function of vertical distribution. So basically, we want to know, how is the urban air chemistry changing over day and night, over a season, and also over multiple years, thinking about how the emissions are changing. We have warmer temperatures. It means we have more molecules also in the air. And so now we can look at this data from the plane, from the ground site, and actually be able to explain, okay, how are these molecules behaving? Are they disappearing? Are they reacting away? And are they forming aerosols? And we also were able to catch a forest fire during that time. So we have very valuable data on the chemical composition through these flight measurements as well. So you can imagine that takes a lot of preparation, definitely takes a lot of money. Usually we get money from the government to make these measurements. And in this case, there was just also a little bit of money here and there that I was able to put together to take part in this particular campaign. Okay, so this is like the top down, but we also have a bottom up approach in my lab. And this is now using our toolkit as chemists. How do we then take single molecules and build complexity to then better understand the real complex atmosphere. And the idea is that the top-down approach and the bottom-up approach are going to merge, and that way we have a continuum understanding of the fate of some of these pollutants and some of these molecules in space and time. So what we do for bottom-up approaches, we tend to use single molecules. So sometimes we synthesize these molecules, so there's an organic chemistry perspective to it. I've drawn here 4-nitroazoles. These are molecules that are very common in forest fires. And this nitro group does really interesting chemistry and photochemistry that we're interested in. We also make particles or nanoparticles. So you can see very interdisciplinary because we want to try to understand how the particles in forest fire smoke are impacting the cloud formation. We also use lots of separation techniques and analytical techniques to try and build complexity. So this is an example of a molecule of lignin from, again, the context of forest fires. So these are the two approaches. And as I've shown you already, this is a picture of my lab. And maybe I have a few more pictures. I want to show you this chamber that we've built. And this is the work done by a master student, Ricky. And we have our atmospheric beakers in our lab, and we have some what we call small beakers because they're about 0.5 meter cube. And we call them pillow bags because it's 2 pieces of a very specific plastic. This plastic is actually a fluoropolymer, and we want to make sure that this plastic is not reactive with ozone and with the molecules that we put in. So it's expensive plastic, but we have 2 pieces of plastic and we blow it up like a pillow. And so that's why we call it a pillow bag. But sometimes the molecules are not very reactive and they last longer. So we need a larger volume so that they don't interact so much with the surface. And so this is the 8 meter cube smog chamber that we built in my lab. And if you are in my 121 class, section 199, I'm going to send out information about doing a tour of my lab. But if there's a few people that are interested that are not in my section, maybe I can send the information, or you can find a friend that is in my section. And I would be very happy to also give you a tour of this lab so you can see this instrumentation. But what is special inside is that we built this chamber with LED lights. And this is very exciting. We're the only ones in the world to have this set up. And it means that we can do wavelength specific. Because LEDs have a very narrow light output, we can have very specific wavelengths. So we can turn them all on and mimic the sun. We can turn some on and mimic only the stratosphere, only the troposphere, only indoor air or indoor light. And so now we can, I think it's very cool because we can really target the atmospheric process that we want to study with these different lights. So that's very much from the instrument development side of things. I've told you already a little bit about how we look at these aerosols and how we're looking at cooking, so like kind of indoor exposure to these molecules. I've told you about my favorite instrument, the SuperNose, and how that works. And so let me come back to my overview of these different different fields or these different research programs in my group. And in the last 5 minutes, and I'll leave some 5 minutes for questions, I want to tell you a little bit more about a project in indoor air chemistry. So one thing, and this is related to the campaign for which we went to Toronto last summer. So one thing that is becoming evident as we're bringing policies to reduce the pollutants in our atmosphere, our air is becoming cleaner and cleaner and cleaner. Now that's without the forest fires, of course. What is happening is that these molecules called volatile chemical products, so molecules from pesticides, from coating, from cleaning agents, it's always smells when you're like cleaning, right? Or even personal care, the smell from your shampoo, from your deodorant, from your fragrance. these molecules are now having a disproportionate impact on air quality outside because the humans are now a big contributor to these molecules. And this was always true, but there's two important factors that are making this pathway even more important. One is before we had a lot of pollution from the cars and from gasoline exhaust and diesel exhaust, and that's been reducing quite a lot. And two, we have warmer temperatures, and warmer temperatures means more of these molecules in the atmosphere, and that can be a problem. So we're interested within this class of volatile chemical products, specifically personal care. And so what do personal care products look like? I've put in here 6 examples of molecules that are related to personal care. So here we have these siloxanes. We see these molecules all the time in our instrument. We can smell your deodorant very, very easily. And then we have these other molecules, some of them are chlorinated, for example. So the study, and actually this is accepted now, so that's the paper that's coming up for my group in the next 2 weeks or so. But Ayomi Day, who's a PhD student in my group, she was interested in Obsession Just for Men by Calvin Klein. And we were interested in the musk smelling molecules in this perfume. And we were specifically interested in these molecules because we expected them to be long-lived. We didn't think they were going to react very fast. And the longer you live in the atmosphere, the more impact you can have on outdoor urban air quality. And so she identified these different molecules in the spray. So you can see here, as a function of time, the perfume is sprayed, and you can see these molecules appear as a function of time. And so what she found was that she oxidized these molecules with ozone. And then there's this key molecule, cashmeran. And we've become very interested in this molecule. It's one of the dominant musk-smelling compounds, but it's very unreactive towards ozone. It takes months, and this little symbol here represents lifetime. So this is going to stick around for quite a while. We also found that actually, as it was being oxidized very slowly, it was producing more oxidants. And so what we identified was a new path for oxidant formation because of the slow reactivity of this molecule. So that was one thing that we discovered. And then the other thing we discovered was that, okay, if this molecule is long-lived and we put it on our clothes and we go outside, we're probably transporting that molecule outside, right? And so we sought out to prove that. So this is work done by Ayomi Day and Clemence, who was an undergraduate student in my group 2 summers ago in 2023. And they hijacked my office space. This is the same, the same frame here. So they came in here, they brought the instrument here, the mass spectrometer, and they used a lab coat and they sprayed the perfume on the lab coat. And what they saw was that the perfume increased. You could see the concentrations of cashmeran here. And you can see that cashmeran was very long-lived. It just hangs out. And then what we did is we took out the lab coat and the concentration goes down. And then we reintroduce the lab coat and the concentration comes back out. So this is what we would expect. We can even smell it, like our nose is a good instrument in this case. But we wanted to show that this molecule, it's not reactive, it's sticking to our clothes, and therefore we're impacting outdoor air quality just from these molecules here. So in Toronto, do you think we saw this molecule, cashmeran? We did. And so we were using, again, this SuperNose mass spectrometer. And what I'm showing here is a concentration of cashmeran as a function of time. And this is 1 month's worth of data. So this is time of day. So now we take all the, 30 days during the month and said, okay, at 1 a.m., what was the concentration on all those 30 days? At 2 a.m., what was the concentration at all those days? And what do you see? You see that it was always peaking around 9 a.m. interesting. This is when people would be putting on their perfume and going outside to go to work, to go to school. So we saw this peak, but only during the weekday, because in the weekend, we didn't see that peak at all. But maybe we saw it also in the evening now, around maybe 7 or 8 p.m., which is also consistent with how people would be wearing this molecule. And so this is kind of interesting just to identify this molecule, but it has two implications. One is that the oxidation of this molecule is very slow, sticks around a long time, generates new oxidants that can then oxidize other molecules as well as itself, and therefore disproportionately contributes to ozone pollution production in the stratosphere. And I'll end to say that to try to connect exposure to these molecules and ozone specifically to health, we have this ongoing collaboration with Professor Michael Cole's lab here at the School of Kinesiology at UBC. And what we do is we expose athletes to different concentrations of ozone, and we want to know how is their body recovering due to that ozone pollution. And so this is informing on how we can say, okay, it's a high ozone concentration day in the summer, we're getting really high ozone, you shouldn't run, you shouldn't go for a bike ride. It also informs on how to then help your body combat ozone pollution. So one way is to make sure you're taking lots of antioxidants, so that, like cranberry juice, for example, so that when you're exposed to the oxidants, you're better equipped to recover from that oxidative stress. So I'm trying to show you that there's now this connection, and we work with other groups, both on campus, other universities, and other countries, to try to really kind of follow those molecules along and try to predict now what that impact might be on air pollution. So with that, I'll wrap it up. This is my group saying hello, and I will end it with here my kind of summary of all the research in my group. Okay, happy to take some questions.
Excellent. Thank you so much. If there's any additional questions, we have a couple of minutes. I know some folks might need to run off to their next class, but happy to stick around and answer any additional questions. But we had some great questions in the middle of the talk, so that was fabulous. Let's go to Simon first off.
Hi, Professor Bourdois. Thank you for taking the time to talk to us. I was just wondering, from the recent wildfires, I've seen a lot of people purchase domestic air filters for their home. Do you think those have any significant benefit in health or environmental impact?
I do. I do recommend them. They're a great idea, as long as you change the filter regularly. So what these filters allow, especially for indoors, we do spend a lot of time indoors. You want to minimize the number of aerosols that you're breathing. Now, I also want to make the distinction between an acute exposure and chronic exposure, right? Nobody is going to die from breathing Brussels sprout aerosols. But if you are exposed to cooking emissions and you work in a commercial kitchen, for example, and you're exposed to those aerosols every single day, there are documented cases of increased asthma among kitchen workers. And so there is a connection between those aerosols and that exposure. So you want to, in general, minimize your exposure. And so during a wildfire smoke, if the air quality is pretty bad outside, I wear an N95 mask. You know, I'm also, since COVID, it's kind of, we all have them. They're kind of easy to get. And then from an indoor perspective, those filters are very useful because what they're going to do is they have a pump, they're going to circulate air through. Usually it's a fan, I think. And then they're going to capture the particles on their filters. So as long as the filters are changed regularly, otherwise then they don't become so useful. But yes, ultimately what you're doing is reducing your exposure to these aerosols. So I think they're great.
Thank you very much.
Yeah, you're welcome. Do you have one? Oh, I don't know. Okay.
Yeah, it was a great question, Simon. Yeah, that's very helpful to know. Yeah, I look for good quality filters in my home. So it's good to know that that's a good approach. Any last questions? Maybe we have time for one more.
Yeah, and I'm happy to stick around also like offline if there's more questions.
Well, we might be at a time where folks have had to run off to their next class, but we had some really great questions, and I want to thank you again for a really excellent seminar.
Yes, thank you. And I'm happy to stick around a few more minutes if somebody wants to ask a question about what we talked about, atmospheric chemistry and things like that.
Sounds great. Thanks, everyone.
I'm just gonna stop the recording.
Thank you.